Sarah, you in 2016 joined the faculty at the University of Florida. And so you started off doing research in exoplanets. You did some work on measuring the radii of the Kepler-19 system.
And the TTV.
And the TTV measurements, so
Yeah.
I do the architecture of that system. You also did some good work with space telescopes and doing photometry using Spitzer and then a lesser one, Proxy. And now Sarah's focus is studying the demographics of exoplanets. Now we have thousands of discoveries. What are those revealing about the formation of planets, the evolution of their architectures in time, and what impacts will happen on habitability. So let's welcome Sarah, and look forward to hearing about your research.
Thank you. Thank you all so much for hearing me. I hope the mic is working okay. I was thinking to myself about the last time that I gave a talk in this room, and I actually think it was 2012 when I was delivering my PhD dissertation. And when I crafted this talk, I like to start by giving a sense for the field, an overview sense, using a metaphor that I first used when I was an undergraduate, actually, for what it feels like to accrue a deep understanding of any topic. I've hinted at it here, sort of with this image at the bottom of rocks underwater. The title of my talk is Day and Night in the Milky Way, the Dynamics of Planets Orbiting Small Stars. But in order to contextualize why one might craft her research program around that idea, I think it's useful to describe that metaphor. So the way that this professor at Berkeley described it to me was that at first, in your endeavor to understand astronomy, in your endeavor to understand anything, it's a wide open ocean of things that you don't understand. Followed by, you've taken a few courses and you see sort of outcroppings of understanding. But the landscape by which those ideas are connected to one another is still largely hidden from you. And as time goes on, you begin to understand not only the fuller topology of the field, of what defines the field and what the big ideas are, but also how those ideas are connected to one another. So to situate my talk until one, ideally knows everything, perhaps not knowable, right? But until one accrues a more or less complete understanding. And so I want to sort of situate the problems that I'm working on within this metaphor in the last 15 years of exoplanets. So this is roughly when I started my PhD, the things that we knew. At least 1% of sun-like stars host planets. So the very first detection of an exoplanet already, we knew the solar system blueprint was not universal by virtue of the fact that it was a hot Jupiter detection. And at this point, we had a lot of hot Jupiters, enough to assert that they exist around 1% of sun-like stars. It might have even been 10% of sun-like stars, or so it seemed at the time. That it was possible to detect the atmospheres of planets. This is first from roughly 2002. Actually, it was the detection of an atomic line of sodium. But the fact that these atmospheres were knowable dates roughly back to this time. Not only that stars host planets, actually the 8th planet to be detected was around an M dwarf, the planets that the stars that I'll be focusing the most on today. So the 8th star detected, the 8th planet detected around a main sequence star was actually detected around an M dwarf. So the fact that stars across the spectral type range all seem to host planets was news at that point. And then also sort of more of the details that would link planetary formation to the outcomes that we see today among mature planetary systems, namely that stellar metal content affects sort of whether planets seem to form. So here we are in 2020. I've shown that the water level's gone down. Water level's gone down a lot. We have this understanding now of sort of the raw occurrence rate in this distribution of orbital period and radius space, which gets used very often, especially with transiting planets, across spectral type. So in that sort of three-dimensional space, radius of planet, orbital period of planet, spectral type. That topology is known. The granularity with which we've mapped it has grown too. I've shown here an indication of the detection of the planetary radius valley, for example, that we've detected dozens and dozens of planetary atmospheres, that the species that we've detected in those atmospheres has become more and more diverse and has actually included particulate sizes, which must be lofted high up in the atmosphere in order to explain their flat spectra. For example, a very recent paper that I'm showing here of one of the first hot Jupiters to be discovered contained no less than 6 molecules in the same spectrum that were detectable. And then after 2009 was really the era in which we started to see images of exoplanets. I had to wrap my mind around the first detection, for example, of a circumplanetary disk, right? So not only a circumstellar disk, but a disk forming around a nascent, probably Jovian planet. And then finally, we were beginning to develop a more detailed understanding about how the contents of the original primordial disk, as probed through stellar metallicity, could be linked not only to whether planets form, but also the nature of their dynamical properties, perhaps how they evolve, among other things. So let me give a very hopeful and optimistic picture of what might be on the front page of the New York Times in 2040, right? Occasionally exoplanets get the front page of the New York Times. For example, well, it wasn't an exoplanet like the putative phosphine detection of Venus, right? That was front page of the New York Times. So if one was going to project this, and I'll be optimistic, we would have information, for example, maybe not on plate tectonics per se, which might be Earth-specific, but certainly we might detect signatures of dynamic mantles on other exoplanets. Even the occurrence of biomarkers, perhaps even beyond the things which overlap with geological and atmospheric processes, to be able to winnow out what actually might correspond to life and what might be sort of degenerate with an interpretation that's purely planetary or geological. I think we'll understand more about something deeply complex, which has outsized importance as I understand it right now, talking with my colleagues in atmospheric chemistry, which is the impact of stellar activity upon atmospheric chemistry and how that might manifest or change the atmosphere over time. And I'll say it, potentially the detection of microbial exolife. So if one wanted to get here in 2040, how would one situate oneself? What sort of research questions might one ask? And I've attempted to craft my research group around what I see as intermediate problems to help us get there. I've described it as establishing a detailed dynamical picture of planetary systems orbiting M-dwarfs, and I'm going to motivate why I say that in just a moment, but just to highlight some of the questions, to give you a sense for some of the questions that my group is working on answering. What is the distribution of orbital eccentricities among planets orbiting small stars? How does that parent distribution look in a volume-limited sense? What are we talking about when we're talking about orbital eccentricities of typical planets in the Milky Way? How might system architectures, the things that we can understand dynamically, imprint themselves upon atmospheric properties? These things are related in ways that in the past we've talked about purely theoretically. But I contend that there's ways to make progress observationally with those things. And then a question I won't be able to get to in my colloquium today, but what a couple members of my group are actively asking is, how dynamically stable are these systems? For reasons I'll kind of get into, that's a suspect notion. How dynamically stable are these systems compared to life's evolutionary timescales? This student, I'll note, just put a paper on the archive today with this sort of toy problem around evolutionary timescales with different putative dynamical sculpting. So why am I talking about M-dwarfs? I'm only going to put one slide. I'm sure you've all have heard the story before. Why would one be interested in planets orbiting small stars? In addition to them being the most ubiquitous type of star in the Milky Way, despite being a human eye being unable to detect even one, they comprise 70 to 80% of the stars in our galaxy. And what was perhaps a surprise, and I think both the nature of the discovery and the surprise of it is encoded in one of my favorite findings from NASA's Kepler mission. This is showing as a function of stellar effective temperature how common are planets. This original y-axis corresponds to the discovery in 2012, but this has since been borne out to an AU or so. And I want you to note the numbers along the top there. And in particular, this corresponded to like the number of stars that went into the sample under consideration as a function of stellar temperature, how many planets. And the Kepler mission was really focused upon sun-like stars. Yet, it certainly seems to be the case that especially for small planets, right, and this is in particular where we had modest completeness, at least at that time, to things that were as small as 2 times the radius of the Earth, they seem to occur with twice the frequency, if not more, around small stars than they occur around sun-like stars. And that combined with 2 things, combined with the ubiquity of these stars in the Milky Way and the relative ease with which we can follow them up and potentially understand their atmospheres, I think that makes them the likeliest subjects for detailed studies, atmospheric studies, especially for searches of life in the next decade. So given that that's true, let me now make an assertion, which is that probably most planets in the Milky Way orbit small stars. I've said the word M-dwarf, I'll be explicit, less than roughly half the mass of the sun is what I'm talking about now. And they reside in a probable likely variety of dynamical states. In around 2017, I saw the field of exoplanet dynamics really shift to using this terminology around AMD. This corresponds to the angular momentum deficit. And as we all learned in sort of orbital mechanics, the maximum possible angular momentum that a system can have is in the circular state. A departure from that system, namely a deficit from that system, would indicate being dynamically hotter. Right? I'll use that terminology because what this is showing is a prediction actually from pebble accretion. So if you had more or less a thermalized, if you can think about it that way, collection of pebbles, what might you expect for how those systems would form? There would be some which have a low angular momentum deficit. So we are talking about a very small departure from the idealized maximum amount of angular momentum, which occurs at small orbital eccentricity. And you would potentially expect to have some dynamically warmer systems. So I'm using the words cool and hot. It's really Scott Tremaine that started doing that, referring to dynamical temperature in exoplanetary systems, which are characterized by a high angular momentum deficit. So why might one really care about this for M-dwarfs? I've contended one should care about M-dwarfs. Why should one focus upon dynamical properties among M-dwarfs? It's because by virtue of these systems being so much less luminous than sun-like stars, the habitable zone is so much closer to the star that dynamics have a really outsized influence when we're considering the habitability of those planets. Work by Rory Barnes and others has argued that even a modest eccentricity, orbital eccentricity around a planet, especially around the later type M-dwarfs, could be sufficient to induce a kind of runaway Venus effect. Right? So certainly Io is not a place where you would expect life to evolve. And then the Jupiter-Galilean moon system is actually a pretty good to scale analog for the types of systems that we're talking about. So that means that if one is talking about planets around M-dwarfs, and in particular if one were interested around the circumstances of those planets and whether they might be hospitable to life, one would be very interested in eccentricity. I'm going to start with what's known. And sort of summarize my own entry together with John Johnson into this field. I'm not going to look at this axis first. I'm going to look at this one, which is mutual inclination. This is showing a top-down view sped up by a factor of roughly 1 million of a real Kepler system. It's Kepler 11. So this one doesn't necessarily orbit an M-dwarf, but it's pretty characteristic. So here we have 6 planets. And one can imagine, based upon the coplanarity of those planets, that the Kepler mission would have detected one or more of them to transit. This is a very dynamically cold system. It should reside down here, right? So if one were attempting to map this space, there ought to be a way to reverse engineer the yield that we have of the number of transiting planets per star to get out this distribution. Is it consistent with what we expect from pebble accretion or not? You can imagine a situation in which the planets are dynamically hotter. Right? The mutual inclinations are slightly higher. In that case, you would expect less planets to transit on average. Those systems would probably be drawn from up here, where there's a higher angular momentum deficit. So this is work that we undertook in around 2016, and this is the sum total of the data that we actually used for this study. It's a vector, and the vector contains 5 numbers, which is the number of transiting planets that were detected around a given star. We attempted to forward model that in a Bayesian fashion. So if one had to design a stamp of a typical M-dwarf planetary system, the stamp was carved using 2 free parameters only: the number of planets orbiting the star and their typical mutual inclination, and you stamped that star isotropically all over the Kepler field. What would you have expected to see? And what John and I demonstrated is that a single population model didn't do a very good job. So I've modeled this. I've shown the angular momentum distribution as being more or less continuous. And perhaps it is, right? There's a contention whether this is bimodal or more of a smooth distribution in dynamical properties. But I will say, following this paper, only 1 year later was the detection of the TRAPPIST system. So note here the 2 parts of parameter space in which we think M-dwarf systems generally reside, at least as a function of these 2 variables. We're looking at scatter in the typical mutual inclination and the number of planets per star. So the solar system would be roughly here, right? We're talking about much closer in planetary systems typically, but as a rule, we would be here. If you took all of the mutual inclinations between all of the planets in the solar system and plotted them, you would see a Rayleigh distribution, and it would peak at about 2 degrees. And of course, we have 8 planets. So, however, just taking that model and attempting to get back the yield of Kepler planets, you don't do it. I'm noting here the detection of the TRAPPIST system, which resides right about here. Right? So one of the most interesting, one would argue, planetary systems is understandable within this dynamical framework as belonging to this dynamically cool population. So this is purely theoretical, right? So this is supposed to be an outcome of pebble accretion, where what I would contend, based on this framework, is that some population from this dynamically cool shape, low mutual inclination, high number of planets, would be drawn in the low angular momentum deficit space, and the remainder would be drawn from this higher angular momentum deficit space. I'm now going to overplot what we would predict observationally for M-dwarf planets. Now this is work from Katie in the paper that appeared today, and that's showing what we would expect purely observationally based on the mutual inclinations we used from this work. We actually painted on eccentricities from FGK dwarfs at this point, but we weren't necessarily sure whether we ought to do that. And I would say one of the biggest questions is the provenance of this. Dynamically hotter systems are roughly 80% of stars, in the sense that they're roughly 80% of M-dwarf planetary systems. You've often heard like a typical number, like 2.5 planets per M-dwarf, right? And perhaps better said, every M-dwarf hosts a planetary system of some kind. And among the types of systems that it hosts are some which are dynamically warmer and others are dynamically cool, perhaps with habitability favoring one over the other, although I'm really waving my hand there. A major question that I'm interested in my research group is the provenance, like I said. Is this completely baked in from planet formation? Is it possible that there's movement to this space over time? There was a paper from Pu and Wu in 2015 that posited that most of these compact systems are actually only metastable at birth. So if that's the case, and I've attempted to provide a picture of why this is interesting, if one wanted to develop a coherent picture of M-dwarf planet dynamics, we're not talking about single planets anymore. That picture needs to be consistent with 3 pieces. One of them is precision constraints that we have on individual systems. So any good model should predict several things. One of them is it should replicate the systems that we understand in more detail. It should predict the things we see at a demographic level, and there should also be a robust theoretical framework by which we can interpret the things that we're seeing. And the members of my research group are working on projects that populate this space in different ways. I'll be focusing on a couple of them today. Sheila Sager is working on eccentricities of individual transiting planets from Kepler. Chris Lamb, who's CCA, actually Sheila is going to be a CCA predoc in the spring. Chris is a CCA predoc right now. He's also an NSF fellow, exploring dynamical timescales that are consistent with the demographic information that we see. My very first student, Kadri Chance, now a finessed fellow, is working on N-body formation simulations, also the effect of binarity, a very big deal for small stars. And my newest student, Natalia Guerrero, is working in this space between precision constraints and theoretical constraints, thinking about the link between orbital dynamics and day and night cycles. That's sort of whence the title of my talk that I'm going to get to eventually. So let me return to these questions. I'm only going to get a chance to really show what my research group has been working on for 2 of them. And the first one is this one. What is the distribution of orbital eccentricities among planets orbiting small stars? Here we are really highlighting Sheila's work. This is an observational finding. It's typically very time and resource intensive to measure the eccentricity of an exoplanet. The gold standard is to do so with radial velocity campaigns. Those can take a very long time, and these are typically quite dim stars. What we took advantage of was an idea that was posited first in like the late 2010s and then applied by Becky Dawson and John Johnson with using the transit duration as a probe via the transit chord to the eccentricity of the planet. And that's because of the assumption that we have about the speed with which the planet is tracing out different parts of its orbit. In a circular orbit, you would expect the transit duration to be drawn from that orbital velocity corresponding to a circular orbit plus the transit chord that should give you some length of time. However, if what you're observing is an eccentric planet, that's really going to change what you see for the transit duration. Of course, one would really need to understand the potential well that that planet is in very, very well in order to predict how it would be moving within that potential well. That's really only enabled by a very, very good density constraint. In the past, this was possible with, for example, astroseismology. Astroseismic density constraints were some of the first studies that used this. But it is the case now with M dwarfs that, enabled by the additional information from Gaia with the distances from these stars, plus spectroscopic data that we have in hand for all of these M dwarfs, Sheila extracted eccentricity posteriors corresponding to this entire family portrait of roughly 200 M dwarf planets. So take a look, right? Any individual constraint is only poor. Right? So we have a sense probabilistically for how these are distributed. There's certainly some which seem to be more eccentric and certainly some which seem to be less. So we asked ourselves within a hierarchical Bayesian framework, what is the likeliest parent distribution from which these eccentricities are drawn? And I'm going to show that here. So for reasons that I've argued in the beginning, we have reason to suspect that single transiting planetary systems and multi-transiting planetary systems may be dynamically distinct. They should be distinct in very predictable ways. What Sheila first encountered for the multi-transit systems is indeed, for these systems where there's very low mutual inclination, they have low eccentricities as well. For single transiting systems, it makes a lot of sense. Well, on average, their mutual inclinations are probably slightly higher, and that's indeed what she sees for eccentricity. I don't have a chance to break down this distribution, but she actually identified evidence that this distribution itself is actually better modeled by 2. Makes a lot of sense, right? Because many single transit systems will be drawn from dynamically hotter systems, and many single transits will simply be bona fide, very flat systems for which we're geometrically unlucky, right? So that means that the single transit eccentricity distribution actually should be a mixture. And what she concluded is that there's evidence at roughly the 20-to-1 level that this is indeed a bimodal distribution with one mode resembling multi-transits and one mode that's much higher eccentricity, and the contribution to those relative modes is consistent with what we expect from the transit yield. I'm now going to show what similar work from Van Allen found for FGK dwarfs. And those are these 2 lines here. Extremely, extremely similar. This is how M dwarf dynamics are interesting, not only to understand from the perspective of habitability, but to understand from the perspective of formation. So if it's the case that whatever is sculpting the eccentricity distribution of small planets, and we were talking about small planets, the sample that Van Allen used, on average 2 or 3 times the radius of the Earth. Similarly with Sheila's sample, typical size is 2 times the radius of the Earth. Whatever sculpts these distributions, it has to be common across spectral type. And there are plenty of things that are not, that you can argue must be operative at perhaps a less important level, and that includes excitation by Jovian companions. That's work that has some theoretical support as well. So from that, we would sort of conclude it's less likely, it certainly seems, using the lever arm across spectral type of how planetary eccentricities manifest. And one could also fold this together with this demographic understanding that we have. So if you had 80% of systems that looked a particular way, and you had 20% of systems that looked another way, in those 20% of systems which are much dynamically cooler, they have smaller eccentricities, there's less of those systems but more planets per system. So what Sheila worked out is in a sort of volume limited sense, what would you expect for the underlying parent distribution? This is in the sense of volume limited, it might be reflective of the Milky Way at large. So we were talking about for a typical sample of 100 M dwarfs, and you were able somehow to extract the orbital eccentricity of all of their planets, I predict that it would resemble this. It's interesting from a formation perspective. It's also interesting because one can identify sort of a priori how many M dwarf planets within a given volume might be inoculated from that sort of tidal Venus effect that I described earlier. We're hopeful that this is useful as a prior for many additional studies, and this is work that Sheila submitted just last week. So I'll progress to the next question, which I want to give a bit of context for. I am extremely excited about it because I think it's a field for which the theory and the observation are both like right at the vanguard at the same time. And that corresponds to how system architecture maps to atmospheric properties of individual planets that might not be obvious why that should be so, especially for individual planets. And let me describe why that might be important, particularly for M dwarfs. So how might it be that our architecture should matter at all when we're talking about atmospheric properties? This is from a Nature paper from Sarah Mulholland showing as a function of eccentricity and now planetary obliquity, what one would expect for the planetary rotation. So I'll say by virtue of the habitable zone being so close in for M dwarfs, you would be really hard-pressed to find an individual working in the field of M dwarf exoplanets who doesn't say they're probably all tidally locked. The planets which are very close in. It's probably very likely they're tidally locked. That circularization timescale is fast, and also the timescale for spin synchronization is very fast. These things should be tidally locked. What Sarah showed is that surely for low eccentricities, it's going to be true that you have low obliquity. The coloring here is showing what you would expect for the frequency, the rotational frequency of the star versus the periodic frequency, the orbital frequency. So a 1-to-1 line here means spin synchronization, aka permanent day and permanent night. This underpins a lot of papers about the potential for atmospheric collapse, for example. So if one were talking about tidally locked planets orbiting M dwarfs, and that was the norm, you had better be able to move hot parcels of air from the day side to the night side before they cool off. Otherwise, you're risking atmospheric collapse. So that's a major question, which has been kind of bumping around in the field for how one might even posit realistic physical atmospheres for these planets. What I want to point out is the following. So the coloring here is showing sort of what you would expect for the planetary rotation rate. If the planet, even for a zero eccentricity, if the planet has a non-zero obliquity, then it is not synchronously rotating. Rather, it needs to be rotating sub-synchronously, which would mean, namely, that the planetary day is longer than the planetary year. Yet, if there's physical reason to believe that this is so, it really merits consideration. I'll say, so this is useful. I am now explicitly linking planetary dynamics to the day and night cycle that we could predict on planets orbiting M dwarfs, which has a lot of implications for life. It's sort of, what's the word, like Armageddon-like to imagine, like the eye of Sauron of a star, which like never changes, and life would have to evolve under its present, constant, extremely hot gaze, right? Although it's plausible, it might even be common. But if we can find a way not only to excite obliquity, but to sustain an excited obliquity for really long periods of time, we would expect something really different for how M dwarf planets rotate. And on top of that, you would expect different tidal properties too. So now this coloring is showing as a function of the same thing, orbital eccentricity and planetary obliquity. The extra contribution that you would get from the planet having a non-zero obliquity to the amount of tidal dissipation that's occurring. So Sarah actually used this result a couple of years later to explain why planets just outside of certain period ratios are inflated. So she used it to predict that these planets which are captured into resonance are likelier to be captured into this particular state with a sustained non-zero obliquity, and therefore would be receiving additional tidal heat due to the obliquity would be deposited in these planets. That's a result which I've heard her say exists with modest confidence, and I think it's really intriguing. So that's two ways that if we can constrain this thing, and we can make a guess about this and how often a phenomena might occur which would excite it, we could maybe say something, not only about day and night cycles, but about tidal heating, even in situations where the eccentricity is very low. And this is where my student Natalia Guerrero is making progress. So I'll say she's right now linking orbital dynamics to day and night cycles using a framework for secular approximations so far, which was set forth by Sarah and Greg in their 2019 paper. So let's go back to this TRAPPIST system and think about what it would look like. This image, beautiful press-generated image of the TRAPPIST system, and so you can sort of see ice crystals indicating out here it would be too cold, and vapor on the inside indicating that it would be too hot, and maybe there's these in the middle that are just right. And that's very interesting because when we're talking about this phenomena, which I'll describe, it is very operative for planets that are close into host stars. And that's not habitable planets around sun-like stars. You are talking about habitable planets around very small stars. which would be sort of amenable to capture into this particular dynamical state. So she argued in this paper they should actually have non-zero obliquities. So with 80% likelihood, she contended, based on just a sort of first-order estimation, based on orbital frequencies between adjacent planets and guesses. So Greg Laughlin actually is demonstrating this part and demonstrating this right here with a top on a plate. So like in real time, he is showing how this particular spin-orbit coupling should look in order to excite a planet into what's called a Cassini state. And in particular, Cassini state 2 is the one that we're interested in here, which is associated with a non-zero obliquity over long time scales, which is what you're actually seeing from that top. Right? In this case, the plate is indicating the precession of the orbit as a whole. The top is indicating the spin precession frequency of the planet. Right? So in order for that to sort of be well defined, we are talking about an oblique orbit. And indeed, you can see how that would be sustained over very long periods of time, provided that these two frequencies were similar to one another. What really intrigued me was that in speaking with Sarah about this, she originally stumbled on the idea, thinking about capture into the Cassini state of Neptune and tilting Saturn's rings, actually in our own system. Cassini state 2 is responsible for the tilt of Saturn over really long periods of time. In order for that to be true, you have to have commensurability between these two key frequencies, one of which is dictated by planetary properties. Right? Like one of which is due to tidal dissipation properties of the planet and the size of the planet, and the other is not due to the planet properties except for their mass and their relative spacing to adjacent planets. So Sarah mocked this up for all of the known multi-planet systems for which there was masses existing from transit timing variations. So she mocked this up. Recall that G corresponds to the orbital precession frequency that she would predict from these planetary pairs. And alpha, she guessed here for a number of love numbers, so she doesn't know, right? And neither do any of us about the detailed tidal properties of these planets. But she argued these frequencies are very, very similar to one another, which means that one might expect, she contended 80% of the time, that you would get excited into this Cassini state, which would map to something really interesting, which is that as a function of semi-major axis here we're showing, what she would expect for the excited obliquity. Now note here that this sample is mostly FGK dwarfs. We know where the habitable zone is, you know, for a G dwarf. If that's one thing we know, it's like 1 AU, right? So that is way, way out here. Where G and alpha, the ratio doesn't work out. In order to excite that non-zero obliquity, they're no longer commensurate. We're talking about very, very close in planetary systems, and we know of some of those. They reside around a lot of stars in the Milky Way. What she showed here is, so she's also taking into account additional non-point source effects, right? So it also depends on exactly how proximal to resonance that you are. When Natalia undertook a follow-up study where we looked at every single M-dwarf multi. So we were just guessing at what the masses are, for example, but we looked at every Kepler and non-Kepler M-dwarf multi-planet system and showed that we expect something really similar for these. What's different is that these planets reside much, much closer to their stars, so that when we're talking about excitation into Cassini state 2, we're talking about day and night cycles on typical potentially habitable planets in the Milky Way. And that's what Natalia is really leading the charge on understanding. What I'm showing here is the work that she replicated using Sarah's formalism from that Nature paper, where she was showing the plausible resonance range that you would expect these planets' obliquities to be excited to. And that's taking into account a lot of the things we don't know, right? One would have to marginalize over a lot of things. Resonance not being possible, that occurs out here. The frequencies are all wrong. And at least there's some overlap here with a nominal toy model of the habitable zone, right? So for sun-like stars, we were so far away that this effect was completely irrelevant to habitable zone planets. Such is not the case for perhaps a third of known habitable planets orbiting M-dwarfs. So how might that map to atmospheric properties? I'll put those on this figure. Right? So based on the work that Natalia did, she determined, well, if excitation into Cassini state 2 is common, and we think that it might be, due to the common commensurability of these two frequencies, a lot, of course, would depend on how they ended up there. We can map them here. We would actually expect these planets to be rotating sub-synchronously, which means that the planetary day is longer than the planetary year. Recall that the typical habitable zone for an M dwarf must be very much shorter than 365 days. And so what Natalia worked out is that if you're talking about the typical orbital period versus the typical, it's covering the axis here, this is the solar day. So the length of time in between like when the sun rises and when the sun sets. And this is showing log in Earth days. So you would have a typical orbital period, for example, of 10 days, and that might correspond to a typical day, which is on the order of Earth weeks. So what we would predict, rather than super rotation, which we are so used to on Earth, namely many, many days per year, what there's plausible physical reason to explore is that sub-synchronous rotation might actually be more common. What that would mean, too, is that these planets are experiencing day and night. Even though that day and night might not resemble day and night as we conceive of it, it renders safer a lot of atmospheres. For example, it also has important implications for tides and tidal heating on these planets. So I'll close with just one idea. So I've shown here these frequencies, and all I made mention of before is just that they overlap, right? So I made an argument, there's rough commensurability. Have a look here at how much these are rotating. So in Sarah's original figure, she showed that the distribution for predicted nodal precession peaks at around 3,000 years. That was her prediction. Relatively short, but we are talking about dynamically packed planetary systems. What Natalia found is that for M dwarfs, typical periods should be something like 2,000 years. Hypothetically, one could measure this. It would take a very long baseline to measure the whole thing. The way one would probe it goes back to Sheila's project too. It has everything to do with the transit duration. If nodal precession is occurring and the transit chord changes across the star, if you have any impact parameter other than 0, that's going to change the transit duration. The question is by how much and over how long of a period of time. Because we do have some baseline between the discovery epoch, I hate to say it because it happened during my PhD, of Kepler, like 10 years, if not almost 15 years, from discovery epoch to now. Should we expect some kind of change? What Natalia showed is if this effect is operative, the nodal precession should be remotely detectable barely right now. So we are newly entering this era in which, so she sort of predicted based on what we would expect for the nodal precession rates, doing our best guess for the nodal precession rates, and marginalizing over the original longitude of the ascending node. Like, we don't know that either. You can make a guess for how much we would have expected the transit duration to change since discovery epoch. For the vast majority of these systems, very, very little. The mean here, because we've had such a short baseline, even though 2,000 years is a fast rate of precession, it's very long for a single human, and especially for a PhD student to be working on. So we're talking the typical delta tau over 10 years, not even a minute, is what we should expect, even if these systems are precessing fast, even if it's happening often. But some fraction of the time, the planets are close enough together, the masses of the planets are high enough, they're proximal enough to resonance, that you would expect a potentially detectable effect, which one could go and measure. That's the case for a tiny subset of them. For example, I'm showing it, this is a KOI here, for example, so we are talking about a very dim M dwarf. What Natalia's done at this point is propose for photometry on the GTC. That's the Telescopio Gran Canarias in the Canary Islands, which is a 10-meter class telescope. That is what one would need to measure the transit of like a 15th magnitude M dwarf. But making predictions, this curve could look all kinds of ways. What we know is that the discovery epoch, the transit duration was this. There's a variety of ways this could be changing. Perhaps it's changing not at all. If that's the case, here in 2023, for example, perhaps we'd be able to see it change. We can predict, if the nodal precession rate is what we think it is, that it should change by an amount that's approximately measurable, given by our precision on the transit depth that we can get from a 10-meter class telescope on the ground of a very dim star, and set by the original uncertainty from the mission, right, with the data that we already have in hand. So this is something that Natalia just did this week, is submit a proposal to gather transits of this sample of planets for which there's roughly 5 in the Kepler sample and 5 which are non-Kepler, mostly detected by TESS. So you can imagine like the baseline between discovery epoch and now is much shorter for the TESS mission and for the K2 mission. So one would have to identify the ability to detect this signal over a much shorter baseline. So we are trying to be very careful about our target selection here. What we have the benefit of here, I didn't put a slide for it, but I'll just say it in words, is the ability to distinguish in a useful way between different things that would induce nodal precession. So because both of these planets transit, in this case, they should trade off, the transit durations should trade off in predictable ways if what we're seeing is excitation from the spin-orbit coupling. It's also possible, my colleague Juliette Becker and others have shown that it's very possible to excite nodal precession, for example, from a giant Jovian planet. However, what she showed is often in that case, systems of very close-in planets are dynamically packed enough that they precess as a disk. If that's the case, you should expect the longitude of the ascending node to always be pointed in the same direction for these planets, and that means the transit duration should change in a different way. So we're hoping to use this as a diagnostic for, first of all, did we get the spin precession rate right in order to make further progress toward, well, if it's close to the rotational spin precession rate of the planet, then we can say something really interesting about whether the most common type, potentially of habitable planet in the Milky Way, is experiencing day and night. I don't have time to talk about the projects that some of my other students are working on with respect to making sure that different dynamical sculpting, if we take a totally agnostic approach to how dynamical sculpting, if it's occurring, is occurring over long timescales, how that should look in planetary systems that's also, we contend, like barely newly detectable. But I haven't had much time to talk about that. So I'll conclude with showing these big questions in my group, and I'd be happy to take your questions.
All right, what questions do we have for Sarah?
Hi, I was wondering,
Yeah, Martin.
very interesting, catching me up on all this stuff I missed.
Yes.
I was wondering about the tidal heating you were finding, how often you got a horrible I.O. situation, how often you got a mild heating that might help prevent atmospheric collapse, or...
So there's two reasons,
habitable zones.
pardon Martin, yeah. There's two reasons why one should be worried about tidal heating here, because this isn't even showing tidal heating due to non-zero eccentricity, right? Which is like the I.O. situation, for example. Like I.O. is not experiencing a Cassini state. You might ask, why is that? In this particular case, it's because J2 actually is dominant over spin-orbit coupling between adjacent planets. So what's showing here is the expected tidal dissipation, not accounting for obliquity tides. Right? So like one would expect for a certain amount of eccentricity, a certain amount of tidal heating. In studies where I showed that kind of skull and crossbones, part of parameter space where that's been said is actually I.O., like the rate of tidal heating of I.O., where it's like absolutely not, probably not habitable, constantly being repaved by volcanic activity, for example, you might not want to visit there. Already that would contribute some tidal heating, yet even for a zero eccentricity planet, you might be expecting a tiny boost. It really depends on how, and note that this is E dot over K, not log scale, right? So you might expect as much as twice the amount of tidal heating that you would expect for a very small, modest eccentricity. Sufficient, Sarah argued, that you should be able to see it with a slightly larger radius of planets right outside of 3 to 2 and 2 to 1. Crucially, that is what she saw. So like just outside of planetary mean motion resonance, planets are slightly larger, and that's a major prediction of obliquity, of heating due to obliquity tides. It should be measurable. And so that's one of the things that made me most excited about this.
Would you expect to see those two different heating effects happen within the system, or do you expect one to trade off against the other? Like, do you want to expect one kind of?
I think a lot would depend. So I like always to go back to the solar system, which motivated me thinking about Cassini state 2 in the first place. Let's go back to the moons of Jupiter, right? So the reason why they aren't tidally circularizing is because of the resonances between them. So a lot would depend on how proximal to resonance these planetary systems are. I don't have a good sense for how their proximity to resonance or exiting therein and thereout would contribute, perhaps in some way trading off between what tidal force is contributing more. There's some numerical simulations on this work in the original Mulholland and Laughlin paper, which I highly recommend. Yeah, Charlie?
Early on, you had this neat result that I had before, that there's two populations of systems with large n and small n.
Yeah.
What's the story for how that comes to be? You might have said it and I missed it. But.
No, I didn't say. And indeed, I hinted at it where I was like, nature or nurture. My computer's gone completely dead. I was just trying to skip some slides, and I'll suffer for that. Okay, wait. Oh, of course, it's struggling so hard. So first of all, I'll say that the bimodal mixture model that John and I invoked, others have said it ought to be a smoother distribution, and perhaps they're right. So regardless of whether it's bimodal or not, what should be the provenance of that? I showed, and Becky Dawson showed, around in 2015 that you could get it just from planet formation conditions alone, and by planet formation conditions, I'm talking about n-body simulations within a disk. So if you vary your surface density profile, the power law of your surface density profile, and the total amount of mass that's available. Becky also tuned parameters corresponding to the gas interaction between the planets. We showed that you can get it just from formation, right? That's plausible. One would expect disks to look a particular way. If that were the case. It's also plausible, my students are working on here, that the 80% of hotter systems are simply older versions of what once were pristine original, and that there's tension there because TRAPPIST is old, right? So but this effect might happen sometimes, and it's certainly plausible based on work of my theorist colleagues that I've seen that the Hill spacing between adjacent planets, people argue whether it's 15 or whether it's 20, and that has a really big difference for what you would expect for whether they're stable on gigayear timescales after birth.
Well, a question from the chat from Roseanne DiStefano.
Hi, Roseanne.
Have you thought about the possible production of the interesting dynamical states you are studying in globular clusters? In 2015-16, Akakray and I considered the survivability of globular cluster planets in the habitable zone of M dwarfs. The work you were describing would add a lot to such studies.
I was thinking about how there was no time to talk about that, and in fact, one of my other students whose work I just referred to quickly here, I heard the word cluster. I'm not exploring stars within globular cluster environments, but I am deeply interested in what proximity to other stars would mean, and whether that has imprinted upon the sample of planets. And in order to understand that, or to contribute to the studies that it sounds like Roseanne is leading, one would have to have a pretty good map for the way that dynamical properties seem to manifest in planetary systems by virtue of how close neighboring stars are. And there's a lot of studies on things like that from adaptive optics imaging, which is stars very far away, and from radial velocity trends, which are stars relatively close. What my student, Kadri Chance, has done is take the reported Gaia RV noise, which is right now the only reported property that Gaia gives for its extensive radial velocity campaign on millions of planets, and reverse engineered it to be a semi-amplitude for all of the stars in the Kepler field. So that's something that he's looking at now, is what is the imprint on stellar proximity to system architecture? Through that angle, I can imagine a connection with proximity in a globular cluster environment. Thanks for the question, Roseanne.
Thank you. Let's talk a little bit about atmospheric collapse. That does seem kind of terrifying. So in the simple naive state where you get tiny loss and none of this good stuff happens, but nevertheless they're not considered to be guaranteed that there will be atmospheric collapse.
Of course.
Right?
Oh yeah, it would depend. So I'll state the simplest possible
The simplest state is
It depends on the mean molecular weight of the atmosphere, and that's because you're talking about a trade-off between advective timescales and radiative timescales. So the question is, the hot Jupiters still have atmospheres, right? So the question here is, can you move hot parcels of air from the day side around to the night side with sufficient time? Well, Correct. Yes. So that's work from Kevin Hang and his student at Hang and Kaparla 2012. Worked it out in just the simplest trade-off between advective timescales and radiative timescales. And of course, it depends on mean molecular weight because of the sound speed. So how quickly you could physically move a parcel of air to the night side. So he actually argued that higher mean molecular weight atmospheres are in more danger. Of course, it would be governed by other things too.
All right, so for the last topic, the observable is a change in the transit duration.
Correct.
Okay. And you made a great case for, the time scale is very long, so what we want to do is go back and look at things discovered in Kepler and remeasure the transit duration.
Sure.
I think that's what we're saying.
Correct.
But I was just curious to know, Kepler did get 4 years of data.
Sure did.
And TESS is maybe going to give us 6 or 8 years.
Yeah.
I just was wondering if you or a student had actually also just happened to go and look at the Kepler or TESS data to see if you were seeing some changes in transit duration that were consistent with these ideas.
So I'll point directly not at your 6, Dave, but at your 5, because Shreyas is working on that exact problem. So he showed me just yesterday decay within Kepler and TESS of a Jovian planet. That's in spiral. So within Kepler alone, you would not expect to see changes on the order of minutes, nor should you if the precession timescale is long enough. And unfortunately, the TESS instrument, while designed to do a number of incredible things, is not the kind of high-precision photometer that Kepler is, which means that the TESS error bars are too big. That's why we're pursuing other platforms. But and of course, there are TDVs in the Kepler sample, right? These don't show them, but they should not.
And this particular example here, you said that there's lots of different ways that
Oh,
this
yeah.
will evolve.
All you know is that it's transiting today, so that the longitude of the ascending node has to be consistent with that. It has to be consistent with the transit duration today.
But
So that limits it.
How typical is this representative of an average of the change that you might see? Is the best case scenario that you might see?
Yes, so the ones that we picked here correspond to 90% of the time or greater, marginalizing of our uncertainty on knowledge of the original longitude of the ascending node. You would expect something more than 2 sigma from the Kepler error bar.
Okay.
So it's 90% of the time is these, so that another 10% of the time, a number of things could be happening. Either G is smaller or longer, such as the case may be, or you're simply probing that part of the curve. You know what I mean? You're probing the part where there's not very much of a change. So this is at the 90% scenario for this particular planet, given that this transit duration is what it is. Yeah, Shreyas.
Yeah, thanks for your talk. I was wondering, in these high obliquity cases, is there some concern that the heating that you get from tides, both eccentricity and obliquity tides, can contribute to unbinding the atmosphere? You mentioned it as sort of a stabilizing effect, but I imagine if there's a lot of tidal heating, that can drive the outflow.
What a good question. I know that it's not work just from Sarah. So Sarah pointed out that there's a particular prediction. It also resolves a long-standing issue with dynamics, which is why are there so many resonances with Kepler planets that are just wide of mean motion? And this is a prediction of that. So obliquity tide should do that. And if that's operative, it should contribute heat at a certain level. She just showed that they're slightly larger. Then work, I think that was led by Eric Pettigura, made an argument about how much larger they should be. I think he said 20%, but that was looking at things that have extended hydrogen and helium envelopes, I think, if I'm remembering correctly. So that question has been worked out, at least at the level of what effects should we see. I don't know if it would have to be so oblique to unbind, right? Because that's just we're talking about a factor of 2, not 2 orders of magnitude,
You have time for one more question?
Just say I really enjoyed giving a talk in this room again. I was thinking about how, in that original conception with the imagery, the future of exoplanets had a high optical depth, but so too did my own future at that point. And here I am presenting my own group's work. It's very gratifying.
Well, let's thank Sarah.